Or I think what I'll do is there's a theorem that they start for the infinite sets and axiom of choice. I'll just write it down because the proof is really tedious and it's pretty much just rehashing all the stuff we already talked about last week. But it is a little useful. So the theorem is if we have A be a set, then the following are logically equivalent. So if we have an injection, and this injection takes the positive integers to our set A, then that implies that you can have a bijection of your set with a proper subset of itself. And of course, in this event, that implies that what we're talking about is that A is an infinite set. Now, it doesn't have to be necessarily countably infinite, which is why this is injective. So if they wanted it to be countably infinite, then this in the positive integers to A would need to be a bijection, because injection allows this to potentially be uncountably infinite. Right. But then the bijection is saying, okay, then if I have this, something smaller than itself, then you can go back and forth between the two. So that would be like taking positive integers, and then a proper subset could be like all of the even positive integers. You can take a bijection. And either way, the original set A was infinite. So there's that. The proof is one of those, it's pretty routine. You basically claim that there's an element, if there's truly a proper subset of A, take one of the elements that's not in the proper subset, but is still in A, remove that, make the map where you shift all of the elements over one by a section, and then reassign that element to.
Similar to last.
Yeah. So that's why I figured, since we actually talked about that one in depth, I won't worry too much about that. Okay, so then the choice axiom is he presented it in actually I'll erase this because it goes good together. He presented it in a very wordy way, actually. It was really crazy. I didn't anticipate it to be like that. So I took it upon myself, instead of necessarily doing an exercise for it, to formalize it in symbolic logic.
Good.
And then also to, if I was going to express it in symbolic logic, find a proof for it in symbolic logic as well. So for choice, axiom of, he distinguishes between the actual axiom of choice versus the immediately following lemma, which is then the existence of a choice function, which is sometimes, those two things are sometimes thought of as the same, more or less, because it follows immediately. But here we have, for all collections A, so long as none of the sets in the collection are empty, that implies that there's going to exist some set C, which is a subset of the union of all of your, of the collection. So A, in script A. And then for all of your sets in the collection, then we have that the intersection between the set and each A only has one element. So choice axiom is saying, essentially, you have a collection of disjoint non-empty sets, and then this is a subset of the union. Every single one of these sets, you're going to take the intersection. You're choosing, essentially, you're making an arbitrary number of choices to take one of the elements to form a new set from your collection. And so since this collection is not necessarily finite, then this is the strong form of the choice axiom. So you can make an arbitrary number of arbitrary decisions.
So each set A you said disjoint? I don't think they have to be disjoint. Right.
The way, so he did the axiom of choice is disjoint, but then the existence of the choice function is not necessarily disjoint. So that's probably the difference. I'll write that one because they're pretty similar in construction. So then the existence of a choice function. So essentially, making decisions can always be described as some sort of a choice function. So in this case, if we have a collection, we call it script B, then now if we have, oh, I think I'm realizing what you're saying, what you're seeing. Yeah, because I guess I forgot to specify here that they're disjoint. Because here they don't need to be disjoint, so I just have to say that they're not empty. Okay, yeah, that's good. But if in this case, so for the choice function, they don't have to be disjoint. Right. So there could be overlap in the different B's. But this will give, instead of a set, a map that lets us go from our collection to the union all over the collection, where for all of the individual sets in the collection, we have that whatever this function, so from here, we're mapping some B, that needs to be an element in this union from B. So essentially, we're able to choose a pairing so that every single set is then assigned to a choice of one of the elements contained inside of that set. So essentially, yeah, it's kind of restating. Yeah, so this is the one that I came up with a symbolic proof for the choice function, which he treats it as a lemma to the axiom of choice in the book, but some other texts actually just start with the choice function as being the axiom. I think the only reason why he made this an axiom and this a lemma is because you can prove this from this, yeah. So I'll make some space for that. This is a good eraser. That's gone. Health 3 classroom needs one of those. Yeah. Yeah. So this is the proof for the function, the choice function. So not the axiom of choice. So we can have, if it's understood that script B is a collection of sets, a collection of non-empty sets, we can have that for all the B in our collection, that we can define B prime to be ordered pair. So we take B with X. And this construction is really nice because what we're going to say is by definition, the X, it will be in itself an element from B. And we can always guarantee the existence of such an element because we're non-empty. Okay. So with this construction, everything kind of falls together pretty nicely because then from here, we can say that we can see if this is like an ordered pair from a Cartesian product. So B prime is really going to be a sum subset of the collection together with the union. Because ultimately what we're doing is there's a sneaky way we're going to make a rule of assignment in order to show that there is a function. So that's kind of where it was a nice callback to the way that he constructed functions earlier in the chapter. And then because we have non-empty sets, so since we've said that the empty set is not in our collection, this tells us that we will always have an X in a B. And if we have X in B, that means we'll always have BX in B prime. And so this is just a little caveat to go from B being non-empty to B prime not being empty either. So we don't have to worry about that. So we've shown non-empty. We're actually going to go back to disjoint because that's when we'll get to invoke the axiom choice. So we can say that if we have two separate ones, so if I got B1 and B2 in the collection, where B1 isn't B2, so these are different, then when we look at the elements in B prime, we have B1 X1 in B1 prime, and then we have B2 X2 in B2 prime. And the issue here is that we can just observe from the way we've done our construction and also from hypothesis that B1, X1 can never equal B2, X2 because we have defined these to be distinct. So there's no instance which you can make an ordered pair the same if the very first coordinates are defined to be not the same. And then from here, since this is true, this is just our little caveat to get around not dealing with issues of overlapping. So these are disjoint sets. So two different sets in your collection B are disjoint. And since we have disjoint and also non-empty, we can define a collection. So we can say, okay, I want to collect and make a new collection, script C, where I take all the B primes as defined from the sets in my collection B. And if I do that, what's going to happen is now I have my two conditions necessary to invoke choice. So there's going to exist some set C, which is a subset of the union of the B primes from our collection C. Specifically, where these B primes in C are that basically, if I were to take the intersection of C with one of the B primes, then there's only one element in there. So I'm only choosing one in that intersection. So this is the choice axiom right here. And from there, we can observe, given these B prime constructions, that they are these ordered pairs, that this set C is going to then contain elements that are of these ordered pairs. So it will be a subset of the script B cross B and script BB. The reason we're trying to do this is because we're trying to show that we have all the necessary conditions for a rule of assignment, where this set will become the rule of assignment given the necessary. So this is the first thing we need to show. And then also, we get the one-to-one from here. So every single one is going to have exactly one ordered pair. And then we note simply that the form of the element to Bx, if this is in our collection, so if that's in C, then by the way we've defined it, X is going to be given to B and B. And so this gives us the existence of a rule of assignment, which is basically a function in this case, of B, script B to the union, where for all of the B's in the collection, we have that what we're mapping, so that C of B, as talked about here, is actually just a member of B. And that's choice function from the axiom of choice.
So the only thing, the B1 intersect B2 is empty. Is that B1 prime, B2 prime?
Sorry, yes, because that would be, yeah.
Now I'm happy.
Yeah, there we go. That would be very different. that would be given from there, yeah. Yeah, the primes. Okay.
Nice.
Yeah, that was a fun one. I enjoyed doing that. It was more so that I could procrastinate having to take the maximum principle seriously, because it had an asterisk next to it. So I'll use it in chapter. I'll use it for Tikhonov.
Oh, okay.
So that's why I figured, well, if I have to learn it at some point, I might as well see it the first time, and then I'll come back to it, review it. and then I'll say, so basically the finite axiom of choice is just simply none. You restrict your collection to be a finite. So, I mean, I don't see why you would do that, because then you're just reducing the generality, but you can do it that way as well. So now he did this because he was running into issues to prove certain things, especially involving like the countability and whatnot, that he was like, he would put in quotes for like the things beforehand, kind of invoking choice. And he left a really funny remark in one of the paragraphs. He said, I have naively asserted that we can make an arbitrary number of arbitrary choices. And he's like, I'm not going to point that out. You just find it for yourself. I, in fact, did not go searching through the text to find where he I was like, you know what? I'll take your word for it. So this is well-ordered sets now. This gets a little bit crazy. But there's some examples I want to do, and then there's one theorem that's actually has a relevant proof in terms of the concept. So first define a set A with an order relation is said to be well ordered if every non-empty subset, non-empty subset of A has a smallest element. So a few good examples, if we were to take positive integers product with positive integers. So if we let X be a subset of this particular set, where we want it to be not empty, so we don't want it to be empty. So then we can express our set X as, A, B, where A and B are both positive integers for some, and then not necessarily, I guess since this is just a subset, I should really specify and say that this is for some, because it doesn't need to be true for all of them. Some A, B, and integers plus. And then what we're going to do to show that it satisfies this property is we can make a set, so we can construct A to be just a subset of the positive integers, because the positive integers is well ordered with less than. So if we take a subset of the positive integers consisting of all first coordinates of A, B, and X. So there's a chain of implications. So the first thing is that since the positive integers themselves are well ordered, then that gives that any, by definition, any non-empty subset of positive integers as smallest element. And so if this has the smallest element, and that's telling us since we have a non-empty subset of positive integers, it has the smallest element. So we could say that, okay, a subset of positive integers where A is not empty, that lets us have A has a smallest element, and we can call it A naught. So A naught in A. And then we could take the set of B's where we take A naught with B, such that B's were found in our original subset. And this is also, this is also a subset of positive integers, because we know this is going to be non-empty because we have this. So I'll say this is non-empty. And then the last thing we can say is since this is non-empty, we have a subset of something that is well ordered. So by the same exact reasoning, we can assert that this particular set also has the smallest element. So we can say that B naught is the smallest element of B for pairs A naught B in X. And so this just gives that the element where we take the smallest that we're guaranteed from here and the smallest we are guaranteed from this set. This is the smallest element of our subset X, a subset of Z plus quad Z plus, by the definition of dictionary order. So the dictionary order that was referenced whenever we did that was relevant.
Right, because it's non-unique. Now, one question, are the set of integers, so the integers by themselves, is that well ordered?
No, so integers are, so there's actually, I could probably prove that from the definition here. Yes, I think I actually can do that. So, because as long as we can find a subset that contradicts the definition. So if I had, oh wait, no, we just did that one. So if we just have regular integers, I can then say, okay, let me make, I want integers X where I have them say negative. And the issue is this is a subset of the integers, but this particular subset has no smallest element. It doesn't have a lower bound. So
okay, good.
Yeah, so then this would not be well ordered. And then so you run into similar issues too, because it's like even so that's with going down to infinity, but you can run into like when we did an analysis, the infimims and supremims. So you could also do, I guess, if you wanted like closed intervals of R. So if I took something like X in R, where we have, let's see, like 1 less than equal to X less than equal to 2, or something like that. Sure. Then I could take a subset X in R, but then instead of allowing the inclusion, just like oops, and then make it like this. So this is a subset of the original of this, but now I don't have a smallest element. So which leads to an interesting thing, right? Because all the countables, so it seems easier to make countable things well ordered with less than, whereas the uncountable, well, this is countable. It just goes down to infinity, but like an uncountable interval. There is, and that there's a theorem for this section that's kind of motivated by that presentation. It's because he's going to work towards saying that there exists basically, for if you have a set, then there exists an order relation such that you have a well-ordered set, which had, its own controversy back in the day. I think it was 1904, something like that. So I'm glad they sorted it out. For the most part, Munkres just said that set theorists today have accepted it as. So pretty much, yeah, if you want to construct a well-ordered set, there's pretty intuitive ways to do it. You can either just take a well-ordered set and then a subset of that well-ordered set. You're still going to have all your smallest elements. And then if you have two well-ordered sets, then just because you take the Cartesian product, then you just switch it over to the dictionary order relation, and then you're well-ordered again. So here, though, here is that every non-empty finite, so non-empty finite ordered set. So not necessarily well ordered, but just ordered, has the order type of a section one to n of the positive integers. So it is well ordered. So the argument he was making before stating this theorem was essentially in the same way that we were taking like how we defined finite sets. If you can take a section and then you get a bijection that way. Then on top of that, so if you do that now on an ordered set and you're specifically dealing with something finite and not empty, then that association between that section, since we've shown in the positive integers to be well ordered, then you also have it an ordered, well ordered subset. So this is a fun one to prove. So we want to show, or we show that every finite ordered set A has a largest element, because if we're talking about the section, we're going to generalize N. And we invoke induction, I suppose, here. So if we have if A has only one element, then this is trivial. Because one element, it's going to be, well, the smallest element is the one element. And then, so otherwise, so since if we're going to suppose, so supposing it true for sets having, and then in a similar way, instead of going n to n plus 1, they just do n minus 1 to n. So having n minus 1 elements, we can let A have n elements and let we need to pick an element in our set, so A not in A. We just pick any element in A, doesn't matter which element this is. This part doesn't have to relate to the hypothesis, because all we're going to do is take this element out of the set to make it to get there. Yeah, so we have then A without the point that we selected has a largest element. And that's true. And we can call this A1, I suppose. And this is going to be true from the hypothesis that the statement is true for n minus 1. So this has n minus 1 elements. And then now that we've identified what that largest element is for n minus 1, we can compare it with the element we took out. And so the larger of the two, so max A naught A1, is the largest element of A. So we've shown we have a largest element if we have a finite ordered set. And then we now show, that there exists an order preserving bijection of our finite set A with the section. That's what we're interested in. So 1 to n for some n. And again, we can in some sense think of it as induction, I suppose. If A has only one element, then again, it's a similar thing. So this fact is trivial, just to map 1 onto whatever you have. And so now we're going to suppose it true again for n minus 1. So suppose it's true for sets having n minus 1 elements. Then we can let B be the largest element of A. So that's, we needed to prove that, so we can just invoke that mini result. So let B be the largest element of A. So B would be max A not A1. And so by hypothesis, there exists an order preserving bijection. Since this has n, we're going to just take out the b. So if we take f prime, we remove our largest element from our set, we can take this to a statement that was true by hypothesis about n minus 1 elements. And then all we have to do is then simply define an order preserving bijection that takes A to N. All we're going to do essentially is just tack back on the B. Right. So we have, since this covers most of it, we just allow f of x to correspond with whatever we mapped from f prime, and let that be for all of the elements that don't include, whoops, it should be an equals thing. So for all the elements that aren't the largest element that we took out, and then for the largest element, just map that to the added, yeah. So then you get that. So we didn't do much induction when we did higher algebra. He's eating it up. Which I do have to say, it is pretty efficient.
He likes it.
So yeah. The one thing that I did not really spend time going over in depth was the recursive definition. Mm-hmm. Just because that was starred, and that's going to be something that not necessarily relevant for the core chapter. So over winter break, I'll probably go back to it, but I've been itching to get to chapter 2. So I'll return as I need. Kind of a nice thing about these. So then there's a few, here's some of the theorems. I won't prove all of these for the reason that some of them are somehow still outside the scope of the text. Never escape that. Okay, so the well ordering theorem is going to say that if A is a set, then there exists some relation, which is an, I guess I should use, just to be standard with the convention here, I'll use like the bracket. So an order relation on A that is well ordering. So that's the one where this surprised me, because then I was thinking about the issues of the uncountability. So if you had reals, then but the issue is this order relation is not necessarily the order relation from which you can have a well ordering. So then it's an issue of finding a well ordering. And he did mention in the book that no one had found a well ordering, I think, for integers cross integers. Which I was surprised by that, because I'm thinking to myself, that seems relatively so who knows? Maybe we can work on that for this class project. Try to find a way to and the reason why it's a little complicated is because it's like we did a well ordering, and it's like a visual diagram for how you could think about doing the well ordering for positive integers with positive integers. But if you're gonna allow going down to all of the integers to all the integers. Anyways. So this was proven in 1904 by Zermelo. So, and the reason why it was controversial is because when he originally did this proof, the only point of contention was he basically invoked choice. And so that's where people have either said, okay, we either throw this out because it contradicts that theory if the choice axiom is wrong, but now that people accept the choice axiom, they accept this. So the corollary that's slightly more applicable is that, believe it or not, there has to then, so there exists an uncountable, yet well-ordered set. It's out there. It's a construction of the consequences of our own actions, unfortunately. So what would they do is to try to get around this, at least the way he treats it in kind of it, is he's going to define X. So let X be a well-ordered set. And then given some element alpha in X, we're going to let S subscript alpha denote the set S sub alpha is equal to X, where the X's are coming from, X so long as X is less than alpha. So this right here is the generalization for when we would take sections of the positive integers. So when alpha, if this alpha was an n, then it's understood to be x, where x's were positive integers such that the x's were less than whatever that is. So this was cool that he kind of nodded back to his own use of section earlier. So it is called the section of x by alpha. And then from this definition, now that we've defined what we mean by here, we can say that there exists a well-ordered set A having a largest element omega such that this section, so if I was to take then S sub omega of A by omega, this is uncountable. But every other section, so because if this is the largest, then every other, so every other section of A is countable. And then the construction is essentially, if I have A being well ordered, and then if we're going to have omega be the largest element of A, then we can describe A as actually being this section of that largest in union with the largest element. And so we're going to use the notation like that. So this is going to be a well-ordered set that is uncountable, guaranteed. Its existence is guaranteed by this theorem.
Okay, go back to the theorem again. So A is any set?
Yes. It just has to be a set. And then the place where it's very flexible is the order relation. So then you'd have to explicitly define and figure out what that such a definition is. So this is more the issue right here. So the set doesn't provide as much of a challenge as finding what relation to make it.
So that's when you do like dictionary orders and stuff like that.
So really we're only interested in, at least with topology, we're going to be doing in point set with basically regular less than and dictionary ordering. But this is just kind of like, there's more stuff out there.
Okay. So the lemma, tell me what that says again. There's a well-ordered set A.
That has, so earlier we proved that if you have a well-ordered set, then you were guaranteed to have a largest element.
Right.
So we're just letting omega be the largest element of A.
Yeah.
But specifically, we want the set to be so that if you take the section of that largest element, then all of that is going to be uncountable. But if you do any other element, so basically you're forced to be less than. So it's basically, he's constructing supremum in a very, very roundabout way.
Right.
Whereas if the moment you take this element out, then all the rest of it's going to be countable. So it's the same thing with like having the difference between less than equals versus less than in the if you're looking at, say, metric topology of reals. So then he's claiming this is the only part where I was just like, I'm kind of trusting him on this until we get to the application of this set. Because it was a random footnote he kind of threw in there. He's like, technically speaking, if this lemma with this lemma, you can take that section, add back your element, and then now just call that your well-ordered set that's uncountable. Nice. So it'd be like probably not the same, but analogous to if you had like, say, a closed interval of real numbers, or if you had it, like a strict ordering. So if it was like less than 4, and then this would be that largest element that if you were to take that section, that'd be uncountable. Whereas the other sections wouldn't. And then you're adding back the element that technically isn't part of that set. And then
I think I'm missing where every other section is countable.
Oh, this, yeah. I'm not 100% sure because he didn't really provide any kind of example other than this construction.
Wow.
So I'm assuming, since this is one of those like starred sections, that 3 chapters later he'll be like, oh, by the way, when we talked about the accountable stuff, here's where it's relevant.
Okay, that's interesting.
But otherwise, I might end up just digging around because this is the only lemma in the sections I did that kind of bothered me in the sense that I never 100% got why that's got to be relevant.
So it's like a comment in the book that says Z cross Z has an order relation on it, but nobody's found it yet.
Yeah, they know that the order relation has to exist if we believe that Zermelo actually proved this.
Right.
But in that case, no one's actually found it. So
with that case,
you would really think that would be found. Yeah, that's what I'm saying. But I can see where by the end of this section, because then this leads right into the maximal ordering and maximum principle. So my guess is he introduced that whole issue to just basically start as the framework from which he introduces supremims and infimims. Where then he's going to start claiming, okay, then we define upper bounds, and then now we're taking least upper bounds. But so maybe because from what it looked like, he was trying to turn the omega idea into the maximum principle.
Yeah, it's some boundary. Usually the omega is a boundary point.
Let's see, because I think I have it on. Yeah, I think it's in this section.
Even in Calc 3, they'll put like the boundary is like delta omega.
Right.
Yeah. So we're doing that in the algorithms right now.
So it's like, if we're given a set, and then we define a new relation. Actually, I was going to ask you because he didn't provide like an English word for this. So it looks like a less than sign, but it's been curved like that. What do we even call that? Other than a strict partial order. I mean, that's the name he gives it in the book.
Yeah, that works. It's used in other contexts, I think, but not usually in the subsetting sense, not the ordering sense.
Right. Well, because when we were talking about having a notation for subgroups, and then for some reason this was taken. Now I know why. But part of me thinks that potentially this is the generalization of subgroup, maybe, because subset is a partial order.
And this might be a link.
So a strict partial order A, if it has the 2 properties. So it's basically going to be the properties that are from the ordering relation, but we're just going to take away the first condition. So we don't require either, X relating to Y or Y relating to X. So we just require non-reflexivity. So A, I don't even know what to say there. I'll just be silent. This will never hold. This never holds. Okay. So that's the non reflexivity. And then transitivity, obviously. So we have A to B, and then B relates to C, and A is relating to C. So this is how they do. I was thinking about that when I went through the order relations. I tried to make subset an order relation, but it wasn't working. It's because it's a strict partial order.
Okay.
So that was kind of a nice little turnaround for me. This is transitivity. So then the maximum principle is stated as a theorem. Well, we're going to let A be a set, and then whatever that is, be a strict partial order on A. Then there exists a maximal simply ordered subset B of A. So essentially, if I were to prove this for the finite case first, you can think of it as essentially I would choose an arbitrary element and then go through the rest of the set and essentially make a map that determines, okay, does this element basically relate with the strict partial order to the arbitrary elements I chose? If it does, assign it to this. If not, assign it to this. And then essentially you're left with all of the points that would have related to that. So then you'll kind of it'll definably be maximal because you'll have checked every single possible element.
Exhaustive.
Now to do that infinitely, then you'd have to invoke choice at that point, because the existence of the choice function lets you make an arbitrary number of decisions. But that's really technical. Anyway, so but from here, let's see what time is it. Okay, yeah, we have time to do up to Zorn's lemma. And then we escape all of this really heady set theory, move back down to some, I think it's just like topological spaces from this section. So we can define let A be a set and let this be a strict partial order on A. So if B is a subset of A, this will look familiar from calculus before. An upper bound on B is an element in A such that for all of the elements in the subset, either we have them being the same thing or less strictly ordered header. And then a maximal element of A is an element M in the set such that for no element A does the relation A. So he's trying to, from what I got, because then I also read a different book. He's just providing the most general framework for the approach. So like I think when we talked about this in Fitzpatrick, he's assuming that we're talking about less than. And so then the upper bound and the maximal element kind of is the same thing, because you're either the same or less than for an upper bound, and then least upper bound idea, or yeah, least upper bound for a particular set was understood to be kind of this maximal element for. So it's like if I had, I think it was something where if we had A, B, and this was in the reals, then this is acting as a maximal element. Depending on what subset you're taking that of. But then Zorn's lemma.
So the maximal element of A.
Yeah. So this is a separate, we're not talking about the subset anymore.
Okay. Such that. Okay, so doesn't have to be unique then?
No. Yeah. And then we can stop here. It's been a lot. Zorn's lemma is that A be a set that is strictly partially ordered.
Okay. I think I see it.
Oh, yeah. So if every simply ordered subset of A has an upper bound in A, then A has a maximal element. So yeah. You have all of your simply ordered subsets. They all have upper bounds as defined by this. Then you're guaranteed to have a maximal element. So that's the relationship, I think, between those two definitions.
Again, my question is, does it have to be unique?
The maximal element?
Yes.
Let's see. Yes, it'd have to be unique. Because this couldn't hold. So we took I think it's the non-reflexivity. It's the maximal element. Like if you had two, if it was not unique, then you could have like an M and an M prime. But then
but it can't be reflexive.
Yeah, you can't. M couldn't be strictly related to M prime, and the other way wouldn't work either.
Okay, good.
Yeah.
So we can prove uniqueness.
Yes. More as a result of the definition. So yeah. Okay. Topology next week. Well,
wow.
So next week is, let me stop the recording here.